In computer networking, Teredo is a transition technology that gives full IPv6 connectivity for IPv6-capable hosts which are on the IPv4 Internet but which have no direct native connection to an IPv6 network. Compared to other similar protocols, its distinguishing feature is that it is able to perform its function even from behind network address translation devices such as home routers. Teredo operates using a platform-independent tunneling protocol designed to provide IPv6 connectivity by encapsulating IPv6 datagram packets within IPv4 User Datagram Protocol packets. These datagrams can be routed on the IPv4 Internet and through NAT devices. Other Teredo nodes elsewhere called Teredo relays that have access to the IPv6 network then receive the packets, unencapsulate them, and route them on. Teredo is designed as a last resort transition technology and is intended to be a temporary measure. In the long term, all IPv6 hosts should use native IPv6 connectivity. Teredo should therefore be disabled when native IPv6 connectivity becomes available. Teredo was developed by Christian Whittemore at Microsoft, and was standardized in the IETF as RFC 4380. The Teredo server listens on UDP port 3544. Purpose: 6-4, the most common IPv6 over IPv4 tunneling protocol, requires the tunnel endpoint to have a public IPv4 address. However, many hosts are currently attached to the IPv4 Internet through one or several NAT devices, usually because of IPv4 address shortage. In such a situation, the only available public IPv4 address is assigned to the NAT device, and the 6-4 tunnel endpoint needs to be implemented on the NAT device itself. Many NAT devices currently deployed, however, cannot be upgraded to implement 6-4, for technical or economic reasons. Teredo alleviates this problem by encapsulating IPv6 packets within UDP IPv4 datagrams, which most NATs can forward properly. Thus, IPv6-aware hosts behind NATs can be used as Teredo tunnel endpoints even when they don't have a dedicated public IPv4 address. In effect, a host implementing Teredo can gain IPv6 connectivity with no cooperation from the local network environment. Teredo is intended to be a temporary measure. In the long term, all IPv6 hosts should use native IPv6 connectivity. The Teredo protocol includes provisions for a sunset procedure. Teredo implementation should provide a way to stop using Teredo connectivity when IPv6 has matured and connectivity becomes available using a less brittle mechanism. As of IETF 88, Microsoft plans to deactivate their Teredo servers for Windows clients in the first half of 2014, and encourage the deactivation of publicly operated Teredo relays. Overview: for a complete explanation, see Teredo overview in external links. The Teredo protocol performs several functions: diagnose UDP over IPv4 connectivity and discovers the kind of NAT present, assigns a globally routable unique IPv6 address to each host using it, encapsulates IPv6 packets inside UDP-v4 datagrams for transmission over an IPv4 network, routes traffic between Teredo hosts and native IPv6 hosts. Node types: Teredo defines several different kinds of nodes. Teredo client, a host which has IPv4 connectivity to the Internet from behind a NAT and uses the Teredo tunneling protocol to access the IPv6 Internet. Teredo clients are assigned an IPv6 address that starts with the Teredo prefix. Teredo server, a well-known host which is used for initial configuration of a Teredo tunnel. A Teredo server never forwards any traffic for the client, and has therefore very modest bandwidth requirements, which allows a single server to support large numbers of clients. Additionally, a Teredo server can be implemented in a fully stateless manner, thus using the same amount of memory regardless of how many clients it supports. Teredo relay, the remote end of a Teredo tunnel. A Teredo relay must forward all of the data on behalf of the Teredo clients it serves, with the exception of direct Teredo client to Teredo client exchanges. Therefore, a relay requires a lot of bandwidth and can only support a limited number of simultaneous clients. Each Teredo relay serves a range of IPv6 hosts. It forwards traffic between any Teredo clients and any host within said range. Teredo host-specific relay, a Teredo relay whose range of service is limited to the very host it runs on. As such, it has no particular bandwidth or routing requirements. A computer with a host-specific relay will use Teredo to communicate with Teredo clients, but it will stick to its main IPv6 connectivity provider to reach the rest of the IPv6 Internet. IPv6 addressing: each Teredo client is assigned a public IPv6 address which is constructed as follows. Bits 0 to 31 are set to the Teredo prefix. Bits 32 to 63 embed the primary IPv4 address of the Teredo server that is used. Bits 64 to 79 holds some flags and other bits. The format for these 16 bits, MSB first, is CRAI. The C bit was set to 1 if the Teredo client is located behind a CONAT, 0 otherwise, but RFC 5991 changed it to always be 0 to avoid revealing this fact to strangers. The R bit is currently unassigned and should be sent as 0. The U and G bits are set to 0 to emulate the universal local and group individual bits in MAC addresses. The 12A bits were 0 in the original RFC 4380 specification, but were changed to be random bits chosen by the Teredo client in RFC 5991 to introduce additional protection for the Teredo node against IPv6-based scanning attacks. Bits 80 to 95 contains the obfuscated UDP port number. This is the port number that is mapped by the NAT to the Teredo client with all bits inverted. Bits 96 to 127 contains the obfuscated IPv4 address. This is the public IPv4 address of the NAT with all bits inverted. Teredo IPv6 addressing table. As an example, the IPv6 address 2001/0004136E378/8063 BF3FFF, FDD2 refers to a Teredo client, using Teredo server at address 65.54.227.120, located behind a CONAT and client is not fully compliant with RFC 5991, probably not compliant with RFC 5991. Using UDP mapped port 40,000 on its NAT, whose NAT has public IPv4 address. 192.0.2.45. Teredo IPv6 example table. There is a JavaScript Teredo IP address calculator available. Servers: for a list of existing Teredo servers, see the list in external links. Teredo servers are used by Teredo clients to auto-detect the kind of NAT behind which they are located, through a simplified stun-like qualification procedure. Teredo clients also maintain a binding on their NAT toward their Teredo server, by sending a UDP packet at regular time intervals. That ensures that the server can always contact any of its clients, which is required for hole punching to work properly. If a Teredo relay has to send an IPv6 packet to a Teredo client, it will first send a Teredo bubble packet to the client's Teredo server, whose IP address can be inferred from the Teredo IPv6 address of the Teredo client. The server can then forward the bubble to the client, so the Teredo client software knows that hole punching must be done toward the Teredo relay. Teredo servers can also transmit ICMPv6 packet from Teredo clients toward the IPv6 Internet. In practice, when a Teredo client wants to contact a native IPv6 node, it must find out where the corresponding Teredo relay is. To do that, the client crafts an ICMPv6 echo request toward the IPv6 node, and sends it through its configured Teredo server. The Teredo server decapsulates the ping onto the IPv6 Internet, so that the ping should eventually reach the IPv6 node. The IPv6 node should then reply with an ICMPv6 echo reply, as mandated by RFC 2460. This reply packet will be routed to the closest Teredo relay, which will finally try to contact the Teredo client. Maintaining a Teredo server requires little bandwidth because they are not involved into the actual transmission and reception of IPv6 traffic packets. Also, it does not involve any access to the Internet routing protocols. The only requirements for a Teredo server are, the ability to emit ICMPv6 packets with a source address belonging to the Teredo prefix, two distinct public IPv4 addresses. The second IPv4 address is needed for the purpose of NAT detection. Public Teredo servers, teredo.remlib.net/teredo-db and .remlib.net, teredo-autotrans.consulintel.com, Teredo IPv6 Microsoft.com, teredo.ngex.ne.kr, teredo.managemedad.com, Teredo Tricks v. Relays. A Teredo relay potentially requires a lot of network bandwidth. Also, it must export a route toward the Teredo IPv6 prefix to other IPv6 hosts. That way, the Teredo relay will receive traffic from the IPv6 host's address to any Teredo client, and forward it over UDP IPv4. Symmetrically, it will receive packets from Teredo clients addressed to native IPv6 hosts over UDP IPv4 and inject those into the native IPv6 network. In practice, network administrators can set up a private Teredo relay for their company or campus. This will provide a short path between their IPv6 network and any Teredo client. However, setting up a Teredo relay on a scale beyond that of a single network requires the ability to export BGP IPv6 routes to the other autonomous systems. Unlike 6-4, where the two halves of a connection can use different relays, traffic between a native IPv6 host and a Teredo client will use the same Teredo relay, namely the one that is closest to the native IPv6 host network-wise. The Teredo client cannot localize a relay by itself. If it needs to initiate a connection to a native IPv6 host, it will send the first packet through the Teredo server, which sends a packet to the native IPv6 host using the client's Teredo IPv6 address. The native IPv6 host then responds as usual to the client's Teredo IPv6 address, which will eventually cause the packet to find a Teredo relay, which will initiate a connection to the client. The relay is then used for communication between the Teredo client and native IPv6 host for as long as is needed. This design means that neither the Teredo server nor client needs to know the IPv4 address of any Teredo relays. A suitable one is automatically found by means of the global IPv6 routing table, since all Teredo relays advertise the network 2010/32. For near real-time information on Teredo and BGP, see the external links. On March 30, 2006, Italian ISP EatGate was the first AS to start advertising a route toward 2001/32 on the IPv6 Internet, so that RFC 4380 compliant Teredo implementations would be fully usable. As of February 16, 2007, it is not functional. In Q1 2009, IPv6 backbone Hurricane Electric enabled 14 Teredo relays in an unicast implementation and advertising 2001/32 globally. The relays were located in Seattle, Fremont, Los Angeles, Chicago, Dallas, Toronto, New York, Ashburn, Miami, London, Paris, Amsterdam, Frankfurt and Hong Kong. It is expected that large network operators will be maintaining Teredo relays. As with 6-4, it remains however unclear how well the Teredo service will scale up if a large proportion of Internet hosts start using IPv6 through Teredo in addition to IPv4. While Microsoft has been operating a set of Teredo servers ever since the first Teredo pseudo-tunnel for Windows XP was released, it has never provided a Teredo relay service for the IPv6 Internet as a whole. Limitations: Teredo is not compatible with all NAT devices. Using the terminology of RFC 3489, full cone, restricted and port-restricted NAT devices are supported, while symmetric NATs are not. The original shipworm specification out of which the final Teredo protocol came supported symmetric NATs too, but this was dropped due to security concerns. People at the National Chiayi University later proposed SymTeredo, which enhanced the original Teredo protocol to support symmetric NATs, and the Microsoft and Teredo implementations implement certain unspecified non-standard extensions to improve support for symmetric NATs. However, connectivity between a Teredo client behind a symmetric NAT, and a Teredo client behind a port-restricted or symmetric NAT remains seemingly impossible. Indeed, Teredo assumes that when two clients exchange encapsulated IPv6 packets, the mapped external UDP port numbers used will be the same as those that were used to contact the Teredo server. Without this assumption, it would not be possible to establish a direct communication between the two clients, and a costly relay would have to be used to perform triangle routing. A Teredo implementation tries to detect the type of NAT at startup, and will refuse to operate if the NAT appears to be symmetric. Teredo can only provide a single IPv6 address per tunnel endpoint. As such, it is not possible to use a single Teredo tunnel to connect multiple hosts, contrary to 6-4 on some point-to-point IPv6 tunnels. The bandwidth available to all Teredo clients toward the IPv6 Internet is limited by the availability of Teredo relays. Alternatives: 6-4 requires a public IPv4 address, but provides a large 48-bit IPv6 prefix for each tunnel endpoint, and has a lower encapsulation overhead. Point-to-point tunnels can be more reliable and are more accountable than Teredo, and typically provides permanent IPv6 addresses that do not depend on the IPv4 address of the tunnel endpoint. Some point-to-point tunnel brokers additionally support UDP encapsulation to traverse NATs. On the other hand, point-to-point tunnels normally require registration. Automated tools exist to make it easy to use point-to-point tunnels. Security considerations: exposure. Teredo increases the attack surface by assigning globally routable IPv6 addresses to network hosts behind NAT devices, which are otherwise mostly unreachable from the Internet. By doing so, Teredo potentially exposes any IPv6-enabled application with an open port to the outside. However, such a vulnerability is an intrinsic effect from NAT traversal. Teredo also exposes the IPv6 stack and the tunneling software to attacks should they have any remotely exploitable vulnerability. The Microsoft IPv6 stack has a protection level socket option. This allows applications to specify whether they are willing to handle traffic coming from the Teredo tunnel, from anywhere except Teredo, or only from the local intranet. Firewalling, filtering, and blocking. For a Teredo pseudo-tunnel to operate properly, outgoing UDP packets must not be filtered. Moreover, replies to these packets must also not be filtered. This corresponds to the typical setup of a NAT and its stateful firewall functionality. Teredo tunneling software will detect a fatal error and stop if outgoing IPv4 UDP traffic is blocked. Also, blocking of outgoing traffic to UDP port 3544 can interfere with Teredo activity. DOS via routing loops. Some new methods to create denial-of-service attacks via routing loops using Teredo tunnels have been uncovered recently. They are relatively easy to prevent. Implementations. Several implementations of Teredo are currently available. Windows XP SP2 includes a client and host-specific relay. Windows Server 2003 has a relay and server provided under the Microsoft Beta program. Windows Vista and Windows 7 have built-in support for Teredo with an unspecified extension for symmetric NAT traversal. However, if there is only a link local and Teredo address present, these operating systems will not attempt to resolve IPv6 DNS-AAA records if a DNS-A record is present, in which case IPv4 will be used. Therefore, typically only literal IPv6 URLs will use Teredo. 1. In the registry at HKEY local machine /system /current control set /services /ntscache /parameters, adding a DWORD value, ADDR config control equals 0 allows the use of a Teredo tunnel for IPv6 connectivity. Teredo is a client, relay and server for Linux, BSD and Mac OS X. NG Teredo is a relay and server based on NetGraph for FreeBSD from the LIP6 University and 6Wind. NICI Teredo is a relay for the Linux kernel and a userland Teredo server, developed at the National Chiang University. Choice of the name. The initial nickname of the Teredo tunneling protocol was Shipworm. The idea was that the protocol would pierce holes through NAT devices, much like the shipworms bore tunnels through wood. Shipworms are responsible for the loss of very many wooden hulls, but Christian Whittemer in the original draft noted that the animal only survives in relatively clean and unpolluted water. Its recent comeback in several Northern American harbors is a testimony to their newly retrieved cleanliness. Similarly, by piercing holes through NAT, the service would contribute to a newly retrieved transparency of the Internet. Christian Whittemer quickly changed the name to Teredo to avoid confusion with computer worms. Teredo navalis is the Latin name of one of the best-known species of shipworm. References. External links: Teredo overview on Microsoft TechNet, current unicast Teredo BGP routes, Teredo MNT, list of operators advertising the Teredo prefix via BGP, Teredo, tunneling IPv6 over UDP through network address translations. RFC 4380, C. Whittemer. February 2006.